With the structure of one-dimensional densities under our belt, we should promptly grasp some low-hanging fruit waiting there for us to pick up. And the structure extends naturally and inevitably to 2 and more dimensions, and let's see how this works. Following the sage advice of the Hungarian mathematician George Polya, we should begin with the simplest version of the problem, for which we do not yet have an answer. And naturally, the simplest step up from 1 dimension is 2 dimensions. So, what would comprise a density in 2 dimensions? Well, naturally enough, borrowing upon what we know from 1 dimension, we will insist upon 2 properties: positivity on the one hand and normalization on the other. We will think of a 2-dimensional function where the variables, naturally and inevitably, we call x and y. We'll reuse notation p for now a 2-dimensional density function, and therefore a 2-dimensional density function, p of xy, satisfies 2 properties. It has to be non-negative everywhere, and the integral over the plane of this function should be unit. Of course, there's an underlying chance experiment we're appealing to, right? Where does the probability come in? Well, the function p of 2 variables stands in the role of a probability density in 2 dimensions, where its units are of probability mass per unit area at the point xy. And where does the area come in? Well, through the terms dx dy. This corresponds to a rectangle, an infinitesimal rectangle of sides dx and dy, and dx dy gives the area of that rectangle. And therefore, all we've said in the integrand is that when you multiply mass over area by area, you get mass. Stitch together the masses using the integral, a stylized summation per Leibniz, and we get a probability mass. There you go. Now, there is, of course, an underlying chance experiment, and we should crystallize our understanding by focusing on it and making sure we understand in just proportion how all these objects fit in. So, let's go back. So we have a density in 2 dimensions satisfying positivity and normalization. What is the underlying sample space? Well, naturally, we have 2 variables, and we're thinking of a composite experiment where the space is a Euclidean plane. We could interpret it geometrically as 2 coordinate axes and the region described by them, and algebraically in the notation which has become traditional for the plane, R2. So in this context, the sample space omega is R2, and R2 means algebraically all pairs of points x, y, where x and y range over all real values. Each performance of this experiment gives us a composite experiment where you have 2 trials which produce values, let us say x and y. So a sample point in this experiment is a pair of real values x and y. Tradition compels us to use uppercase letters at the end of the alphabet to describe these possibilities for the trials. The pair of values x, y then constitute a pair of random variables, and such a pair in this composite experiment describes a sample point of the experiment. What are the events in this experiment? Well, remember, events always are subsets of sample points. What are natural subsets of sample points? Well, they're regions of the plane, and the simplest basic regions we could imagine, building upon the intuition of intervals in 1 dimension, will be a pair of intervals, and a pair of intervals gives us naturally a rectangle. And therefore, the basic events, basic regions, are rectangles in 2 dimensions. We can describe it, of course, geometrically or algebraically as a Cartesian product of 2 intervals, which gives us all pairs of points x, y, where the first variable x lies in the first interval, the second variable y lies in the second interval. Now we want to go ahead and assign a probability to this. How do we go about doing this? Well, by very simply accumulating mass by integration. In notation, the probability that a pair of random variables comprising the composite experiment, x, y, The probability that this lies in a rectangle is the integral, the accumulated mass of your two-dimensional density over that rectangle. There you go. Simple. What about more general events? Well, a generic event in two dimensions is some region, or possibly some composite collection of regions in two-dimensional space. Right? Algebraically, your region A is a subset of the Euclidean plane R2. How do we compute its probability? Well, we could imagine tiling this plane with a lot of itsy-bitsy tiny rectangles, and then simply adding up the masses of each rectangle via additivity. But of course, we'll want to make the rectangles tinier and tinier and tinier, and in the limit, the sum becomes an integral, and what we have, the probability that a random pair lies in a designated region A is the integral over A of your two-dimensional density function. Notice how all the intuition just carries forward. Having got two dimensions under our belt, it is now clear what the general structure should be for many dimensions. Right? The terminology and the notation is going to ineluctably get a little more complex, but that should not concern us. The basic ideas are clear. What should describe a density in, say, some generic number n dimensions? A density in n dimensions is a function of n real variables which satisfies A, positivity, and B, normalization. The integral of this function should be unit. Of course, there's an underlying chance experiment. Where does the probability come in? This density function connotes a mass density, but now it's a density in n dimensions. In one dimension, you have units of mass per unit length. In two dimensions, you have units of mass per unit area. In three dimensions, naturally, you have units of mass per unit volume. And in n dimensions, we will generalize this concept and say this is representing a mass per unit n-dimensional volume at a given n-dimensional point, x1 through xn. Where does the volume come in? It comes in from the product of all those infinitesimal terms. Think of this as an n-dimensional parallelepiped whose sides are dx1, dx2, dx3, dx4, dx5 through dxn. You multiply all of these values out, you get the volume of that parallelepiped, and that is your infinitesimal volume. Mass per unit volume times volume gives you mass, and you're just stitching masses together via additivity. And there you go. What is the underlying sample space here? The underlying sample space is a Euclidean n-dimensional sample space. And again, tradition compels us to write, instead of omega, Rn for the n-dimensional Euclidean space. Of course, the notation looks a little complex to someone who hasn't seen it before, but it describes a very simple object. This connotes a composite experiment where you have n trials giving you values x1 through xn. These values x1 through xn range over all possibilities for real values, and that gives you an n-dimensional space. Tradition again compels us to write the sample points for this experiment using uppercase letters, generically x, but now we have to describe which trial gives rise to which outcome. And naturally, we'll use subscripts to capture this complexity. x1 denotes the chance outcome of the first trial, x2 of the second trial, xn the chance outcome of the nth trial. And together we have a composite experiment comprised of n chance outcomes, x1 through xn. Naturally enough, this describes, in the parlance of algebra, a vector. And therefore, the sample points in this composite experiment are what we call random vectors. It is frequently useful to compact notation and write simply vectors in bold font to represent an n-tuple of real numbers. Okay, so now we have a right understanding of what the underlying sample space is and what the outcomes are, these idealized outcomes of this composite experiment. What are the events? Well, naturally, events are regions in this Euclidean space. So any event A has to be a subset of Rn, and I've given you a fanciful region just to show you a region could be anything you like, over which one can accumulate probabilities in some reasonable way. How do we compute probabilities? Well, probabilities are via additivity identified with integrals. The probability that a random vector, the outcome of this composite idealized experiment, lies in a designated region A is simply the integral of your n-dimensional density over that region. And there you have it. So starting from a process of segueing from discrete experiments to a continuous experiment in the limit, we get a one-dimensional random variable, and from there very quickly we build up composite experiments in 2 dimensions and more. All of these ultimately are probability spaces characterized in the continuum by these functions which distribute mass according to a density, and the density generically has got units of mass per unit volume.